All right, want to do a couple of example problems here, actually just one, and because I think it's kind of hard to do examples using PowerPoint, but I'll walk you through this one example and then we'll work some more when we go back into a live class session. Mostly the PowerPoint's good for covering things that are pretty visual, that don't need a lot of computational or analytical kind of board work. All right, so first of all, I want to talk about the fact that we have been looking at these circuits in a way that's similar to figure 13.7 here on the left. And I think I mentioned in both the lecture and the previous video that we're dealing with AC circuits here. So we'll do the impedance transformation on the whole circuit, giving us a phasor voltage, phasor currents, load impedance, and j omega L for the inductors, j omega M for the mutual inductance. So this is the way we will analyze our coupled inductive circuits. So this is the example that I want to look at, and you'll note on this example we have the dots and we have the mutual inductance specified here as J3. This is the way you'll get that specified in the problem. We have a capacitive impedance, we have a resistive load connected to coil 2. We have two phasor currents defined, and we have 12 angle 0 as our voltage source. So this is kind of how the problem would be presented to you. You know, if the inductors couple, that it's got to be AC, because even though the inductors couple on a DC as far as sharing flux, they don't induce a voltage because there's no time variation. So the inductance effectively in a DC circuit looks like a short. So this is an AC circuit. It's already been converted for you to the phasor domain. And so now we just want to find out what the phasor currents I1 and I2 in the circuit are. Now, if all you had was the circuit on the left, you would write an equation that says minus 12 angle 0 minus J4 times I1 plus J5 times I1 is equal to 0. And that would be your mesh equation if you had no coupled inductance. However, we do have coupled inductance, so we have to take into account the mutual term. So the first thing we want to look at is, as the problem has been set up here, I1 enters the dot here, which means it'll induce a positive voltage over here. But the mesh that we're actually writing is we're writing the mesh for we're writing the KVL for the mesh that contains I1. So what we're interested in is what is the induced voltage by I2. So if you look at I2 actually leaves the dot in its side of the circuit. So what that means is the voltage that is induced by I2 in mesh 1 will be negative at the dot in mesh 1. So what we'll actually have for the mutual term is a minus plus across this inductor. Now some people will illustrate that as a dependent voltage source, and they'll actually draw in the dependent voltage source in series with this inductor with the correct polarity. But that's not essential. We just need to remember that we will have a negative voltage at this terminal and a positive voltage here. So what that means is that is a voltage rise for the mutual term. Also remember that it will be equal to J3, the mutual inductance, times I2, the current in the other mesh. So let's come look here at the equation that's actually written. So we have our minus 12, that's the voltage source, so clearly we're summing voltage drops. Then we have a drop across the minus J4 impedance, so we have minus J4 times I1. We have a drop across the inductor, so we have a J5 I1, and that's positive because it's a drop. The only reason the J4 is negative is it's a capacitive impedance. And then we have to incorporate the mutual term. Now, because the mutual term went from minus to plus on this inductor, we're going to have a minus J3I2. So that's going to enter as a rise in my equation where I'm counting drops as positive. So we then simplify that and we get, notice for a single mesh, we get that's actually not physically connected, we get an I1 and an I2 term because it's inductively coupled. Now let's look at coil 2. Without the coupling, summing voltage drops, I would have a J6I2 and a 12I2 summed together in the equation. However, I need to incorporate the mutual term. So I1 goes into the dot here, which means the mutual term will be a plus at the dot on the right-hand side of the circuit. So I'll have a plus minus. Now, as the current I2 goes around and I'm summing voltage drops, since the plus is at the dot for the mutual term and the minus is here, that's actually a rise. So if I'm counting drops as positive, that term is going to enter as a negative J3 times I1 because I1 is the current that's actually doing the inducing. So if we look at that particular equation, we have the minus J3I1, that's the mutual term, and then we have 12I2 for the drop across the resistor and J6I2 for the drop across the inductor in circuit 2. Both of those multiplied by I2, both of them positive because they're drops. So we can rewrite this expression to put I1 in terms of I2. We can rewrite this expression to put I1 in terms of I2. And then we can do some algebra setting the two I1 terms equal to one another and getting a solution. We'll get I2 is 12 over 4 minus J, which if we then do rectangular to polar conversion, we get 2.91 angle 14. If we then substitute into either of those equations for I2, we can get I1, which is shown as followed. So really, there's nothing new as far as how we write our mesh equations. We're still counting voltage drops as positive. We come in, we define our currents. You'll notice they're defined in the clockwise direction, which is not essential, but is a good idea because it kind of keeps things consistent in how we write our mesh equations. And then we have to incorporate the mutual terms. So the only new thing, if I go back one page, the only new thing in this example is this minus J. I'm not very good at using this pen on the screen, but this minus J 3I2 here in mesh 1, and the same thing here in mesh 2. So that's the just one example that I wanted to show you, and when we get back and meet again as a class, we'll work a couple more. Thanks.